welcome to what is unfortunately already the last day of this beautiful workshop. So the first speaker this morning is Stephen Evans of the University of California at Berkeley, and I'm sure he will explain to us whether his title is religiously, biologically, or mathematically oriented.
With that's practical advice. So thank you very much, Anna, and thanks to Peter for organising this wonderful meeting, and also of course to the Institute for sponsoring it and hosting us. I was just talking to Sergey and just wondering if anybody recognises any of these three individuals here. There we go. Is that better? Okay. Sorry. So that's actually Lyapunov. This is an acorn woodpecker. And that's Frobenius, who's going to show up, hopefully, towards the end of the talk, not because of the Perron-Frobenius theorem, but because of his work in group representation theory. So this is a joint project that we're still very much in the middle of with a graduate student of mine, a former graduate student of mine who now has a postdoc in the Department of Evolution and Ecology at University of California at Davis, and one of his postdoc advisors, Sebastian Schreiber, who's also in that department, but who started out life actually as a PhD student of Stephen Smales, doing dynamical systems, and then sort of moved into doing, deterministic dynamical systems in biology, but is now, population dynamics, but is now very interested in stochastic things. Okay, and so the basis for what I'm going to talk about is that organisms live in environments that certainly change both as time passes and as one moves about space, and those environmental conditions certainly very much affect the organism's ability to survive and to successfully have offspring. That's what fecundity means. And so organisms then have the possibility of trying to modulate their fitness by not just staying in the one place and accepting what life throws at them, but by moving around, trying to sort of find perhaps a better life, or not necessarily, even deliberately moving around, but I guess I could go to another biblical thing. There's the sort of some biblical parable about seed falling on hard ground and soft ground and all that, but that is what trees do, right? The trees know because they're growing somewhere that they're probably, because they're growing somewhere they're probably in a fairly good place to be, but they sort of disperse their seed, this is a good bet hedging strategy because sometimes the seed will fall in places that most of the time is maybe not so good to be if you're attempting to grow as a tree, but every now and again it will be better there than where the parent was, and so there's this kind of not putting all your eggs in the one basket thing. So my co-author Sebastian's a bit younger than I am, and so he, as an aficionado, I guess, a clasher from the 80s, are they? So, sort of after my time of kind of interest really in popular music, I guess. But, this does sort of express the quandary that organisms find themselves in. And so, a little more formally, that's the question that one wants to answer. Okay, so let me sort of begin with something that I'm sure everyone in this audience knows. Let's just imagine that we had a very simple model for just the growth of a single population without any spatial structure or anything like that, and that this was something that we thought of as evolving in discrete time. And so, we had the concept of the per capita fitness of individuals in that population in year T, and that we were going to treat these things as just IID random variables. So, the sort of conditions where these individuals live from year to year, they're just going to be something that evolve, in that IID way. And, fitness is something that we'll interpret as, being like a per capita growth rate. And so the sort of number of individuals, in some sense, that we have 1 year later is just the fitness in the year times the population size at the start of the year. And, well, we all know just from the strong law of large numbers that if we want to understand what how this process sort of evolves as time goes on, that if we just take logarithms and divide by time, then just the strong law of large numbers tells us that this quantity will grow like that. The first thing here, okay, and so this is just saying that essentially the population size grows exponentially, but with a rate that's sort of given by this formula rather than the logarithm of the expected value, right? You might think if on average the population is doubling every year, then it's going to grow at a rate of 2 to the t, but that's we all know that's not the right answer. And in fact, the right answer for the growth is something that's smaller than the answer that you would get from that naive guess that I just mentioned. And this was something of a surprise for even some very smart biologists, Lewin and Cohen, that they realized that this phenomenon was present, and their way of expressing this, what we'd say, well, this is just a consequence of Jensen's inequality. As they say, it's the difference between the geometric and the arithmetic mean. And so, if you're interested kind of in the long-term fate of this population, then this is the quantity that you should be interested in. Okay, so now we can get to looking at an actual population. So this is a population of these cool animals, acorn woodpeckers. I don't know if any of you have ever seen film of them on TV wildlife documentaries, or if you've seen them in the wild, or you don't even need to have to go in the wild. They're sort of like round, for example, the Stanford University campus everywhere. They actually peck holes in trees and then store acorns in the holes, and then are constantly readjusting the acorns and to make sure that they dry properly, etc., as they store up food for the winter. And so, of course, a naturalist can go out in the field and sort of try to count how many of these guys there are in an area, how many are born each year, and all that sort of thing. And so when they do that, they can try to come up with estimates of the fitness in this population. And of course, I'm being rather fanciful here. We don't exactly have a large number of years, and there's not a huge number of individuals, and so the sort of model that we had of just sort of taking the current population size and multiplying by a random fitness may not be so appropriate at this population size, but I'm just sort of putting this up here as kind of an example of the sort of thing that sort of field ecologists do. And you get a negative number. It's not very negative, of course. And so the question is, well, this, if the model really applied and this really was, our estimate of really was what the rate was, then this population would be heading towards dying out in this particular area. And so, because what we've done here is, treated this canyon as being completely isolated, and I'm not actually sure whether it is or not. They don't mention anything to do with immigration. They mention emigration, but not immigration. And so the thing is, can populations actually get round this problem of, if you were to just stay in any particular spot, you'd be headed towards extinction, but by, dispersing and using, some degree of independence between various locales, you can actually get a positive growth rate. You can overcome this problem. Okay, so I'm going to talk about that in the context of a continuous time model rather than a discrete time one, because for one thing, the mathematics becomes much easier. And so the word that the ecologists use for, sort of little locales within an environment as patches. So, there's sort of n kind of identifiably different places where individuals live. And we'll sort of have this notion of the kind of cumulative fitness up to time t in the ith patch. And so this guy here is in some sense sort of like the instantaneous fitness at time t. And we'll imagine that this looks like that. And so this is just a way of saying that on average the population in patch I is growing at rate mu I. Okay, but then we'll think that there's some randomness going on, and so the correlation between these values in patch I and patch T is going to be given like that, just for some matrix gamma, and then we'll assume that these instantaneous fitnesses evolve in such a way that what we see at a particular time is independent of the past. And of course everyone in this room knows how to turn that somewhat informal description of a model that you present to a biologist into mathematics, namely that we think that this guy is just growing as a drifted Brownian motion, okay, with some mean vector and some it's a Brownian motion with a non-identity variance-covariance matrix, and of course we can just produce that by taking a standard Brownian motion and doing suitable linear combinations in such a way that this matrix sigma has the property that sigma transpose sigma is the variance-covariance matrix gamma that we had up here. Okay, and we'll write that in this form here, and the ecologists seem to like representing their population counts in column vectors, and so let me just stress that we're thinking of these things as column vectors at the moment, because that will sort of become a little important next. Okay, well, all that is just describing the environment, and now we have the individuals living within that environment, and they're going to be moving around. And how do they move around? Well, we're going to picture that there's some rate at which individuals in patch J disperse to patch I, so we'll call that dji for dispersal, and adopt the usual kind of Q matrix generator convention that we turn these things into a matrix by putting the appropriate negative numbers down the diagonal. Okay, and then how's the population size in patch I going to grow? Well, it's going to grow by just this kind of local exponential growth determined by the instantaneous fitness, plus something that's given by the effect of inflow via dispersal from outside and outflow via dispersal from state I to other states, which is because conveniently why we adopted that convention up there. And so we can just summarize that all in a vector equation where it just looks like this, where the little diamond notation here is just take two vectors and multiply them coordinate-wise. I mean, that's usually a little circle's used for that, but stochastic analysts would get very confused if you did that, because it's the same notation for Stratonovich sort of integrals, so we've forsworn doing that. Okay, and I sort of don't expect you to be able to read this, but it's just, yes, suitable data can be collected to try to fit models like this. This thing here, this paper, is just a one-patch situation, not where there's a whole geographic array of patches, so it's just a one-dimensional model. But again, it's of that SDE type form that I had, and so you have this lovely thing. You probably can't see the keywords down here, but you have stochastic differential equation, stochastic population model, hooping crane, Wiener process, and Puerto Rican parrot, so it's pretty cool that you see all of those things in the one place, right?
Journal that comes from, what's the name?
Ecological Monographs, and it's 1991, I think, yeah. And and it's great to read, right? Because just sort of like any applied literature, because they talk about the difficulties in fitting their model, for say the Puerto Rican parrot, because of minor things like the arrival of Hurricane Hugo sort of tends to mess up the assumptions of the model, right? So let's get back to the model that we had, and so this is just a linear stochastic differential equation. And so, really, one way of thinking about this is if you were to just discretize time and look at the vector of population sizes at time k, then the way that this arises is just by taking the original one and, multiplying it k times by a bunch of IID random matrices that are, can sort of be constructed from the flow represented by that linear SDE. And, so you can go to your, sort of favorite random matrix book, for example, a book by Hergness and Mukherjee or something like that, and see that, for example, if we look at the total population size, then for such a model, the total population size will, grow exponentially, in the sense that after we take logs, it grows linearly to, with some rate chi. And many ways of thinking about this result. The way that this sort of thing is proved is now usually just as a very slick application of the Kingman subadditive ergodic theorem, but you can think that it goes back to sort of the oscillated multiplicative ergodic theorem. It's a sort of special case of that, and of course that result itself is after Raghunathan's work is usually proved using Kingman. And it's also, related to the Furstenberg Kiefer theorem about products of random matrices, which was again originally proved by different technology. And so, as I said, that constant chi has the name the Lyapunov exponent for the process x. And we sort of have this nice warm feeling now, except how do we compute this thing? Before, if we were just in one dimension, we were using the strong law of large numbers, and we just had to compute this thing as the expected value of something. But unfortunately, life's not so simple anymore, and we want to have some way of getting our hands on what chi is. And so the way to think about this is to look at something auxiliary, which is also, of course, something that's of interest in its own right, namely the proportion of the total population that's in each of the n patches. And we can all do the Ito's formula computation, and because the original thing was linear, it's not surprising that y is a Markov process in its own right, that of course now lives on the probability simplex, non-negative numbers that add up to 1, and it's governed by an SDE that looks like this. And so we've got this nice SDE on a compact state space, and if this matrix D here, which remember is a generator matrix of a continuous time Markov chain, if it's irreducible in the sense that we use for generators of chains, then, and also the noise isn't singular, this guy's got full rank, then one can just argue using sort of standard type ergodic theorems for diffusions on Rn, that the law of Yt will go off to some law y hat as time goes to infinity. And moreover, if we look at time averages, so this is just the occupation measure of the process y, how much time it's spending in various places, that will converge almost surely to the law of y hat, this probability measure here. Okay, so now why is that helpful for the total population size? Well, if we go back to the total population size, then just by algebra, of course, we can sort of factor, we can write out the semi-martingale representation of the total population size. Of course, it'd be great if the total population size was Markovian in its own right, but it's not going to be. We do need to know X to know how S involves, but we can factor out the total population size and then have these Y factors here. Okay, and then when you take logarithms, something really beautiful happens, namely that if we look at the log of the total population size, then what have we got on the right-hand side here? Just stuff that involves this process y that's living on the probability simplex and is going to have this ergodic behavior. So if we divide by t and let t go off to infinity, well, this will disappear. Okay, this will also disappear, right? Because, you know, this thing in here is going to have kind of going to have CLT type scaling. And so all that happens is that we're going to get kind of the time average of, you know, this term and the time average of this term. Yeah.
So could you go 2 slides back?
2 slides back?
One.
That one?
Yeah. You said that there is convergence in the Cesare
Yep.
sense, but why you live on the complex set? So why there is no stronger convergence, weak convergence?
Well, no. This, in law, y hat converges in law, right?
Yeah.
And that you don't get anything better than that, right? I mean, if you've got a Markov chain that's just wandering around, right? It's not the sample paths aren't converging to anything, right?
No,
Right.
I said it in law. So no, you said it about Cesare limit convergence.
Yeah, but no. But this converges almost surely, right? This is not the Cesare. What this is the occupation time. So what this is saying is, for any test function f.
Okay.
Yeah.
It's exactly weak convergence. I'm sorry.
Well, no, this is. Yeah, I'm saying this converges almost surely to the expected value of f. Okay? Yeah. So the usual ergodic statement for Markov processes. Okay. So, you know, what I just said there is that we have a nice expression now for chi in terms of you know, the underlying parameters that describe the environment, and just the first and second moments of the limit random variable y hat. So let's sort of see how we can actually put that into practice in the simplest non-trivial example where there's just 2 patches. And let's suppose that you know, there's a variance parameter for the first patch, a variance parameter for the second patch. The patches are independent. Then, of course, y hat is something that's living on the, you know, probability simplex, you know, with, you know, 2 numbers, non-negative numbers that add to 1. So all we need to do is discuss the amount of mass that's assigned to the first patch, and, you know, we can just by sort of one-dimensional differential equations, sort of Sturm-Liouville type things, figure out what the probability density is going to be of that limit random variable, and we get an expression like this, you know, with some parameters that depend on the parameters in the problem. So remember, this is the growth rate in patch 1, the growth rate in patch 2, the rate at which stuff is going from 2 to 1, the rate at which stuff's going from 1 to 2. Okay, and so this is, you know, the sort of equation that, you know, probably most of us here, we know how to do this once you write down what the usual differential equation is that has to be satisfied by the stationary density. Okay, and so now we can kind of see something interesting. So, you know, let's suppose that we have that model where the variances are the same in both patches, the means are the same in both patches, and the rate of dispersing from 1 to 2 is the same as the rate of dispersing from 2 to 1. So everything's completely symmetric. And first of all, you know, you can look at what happens to the stationary distribution of y1 hat as that dispersal parameter changes. Okay, so when it's really small, when there's hardly any dispersal, the stationary distribution is out towards the extremes, right? So in stationarity, you'll either be highly likely to be at 0 or at 1. But as you ramp up the dispersal parameter, stuff shifts in towards the middle and gets closer and closer to, just a point mass at a half. Okay, and now you can see what happens if we compute the growth rate chi, the Lyapunov exponent chi, using our formula. That we have this nice thing that, as we ramp up the dispersal rate, we go from a situation where the populations would be dying out to one actually where they're going to be increasing at an exponential rate. So, if the populations were isolated, they die out, but when they're allowed to disperse and, not be putting all their eggs in the one basket, they can go to a situation where they can overcome the effect of that phenomenon.
If I go general,
Yeah.
you also have something like perturbed Dirichlet distribution. Or
Yeah, well, were you saying in general?
yeah, for general.
It'd be great if that's true. We weren't able to show that. So if you know how to do that, when we looked at the equations, we couldn't sort of see that was true, that it would be something like exactly a perturbed Dirichlet. Yeah, yeah.
I mean, you got something similar with the stock market, with finance and,
So these equations are exactly the same as the Black-Scholes model for, sort of stock prices, right? Yeah.
Because what you're doing is you're talking more or less about the diversifying into different stocks rather than holding one.
Oh, I guess it is a little bit like that. True. Yeah, I hadn't thought of that. Yeah. Oh, that's interesting. Yeah. Wrong way. Sorry. Okay, so what I want to talk about now for just a few slides is this thing that the first time I saw it, I thought it was something about, kind of members of the Republican Party, this sort of ideal free, but I realized there, it's ideal free dispersal, not ideal free dispersal. And so it took a while to figure this out. But here the assumption is, let's just imagine that the environmental parameters are fixed, and within that fixed stochasticity of the environment, what's the optimal thing for organisms to do? And so, we want the form of the dispersal that will actually maximize the growth rate. Okay, well, if you remember this thing appeared in the formula for chi with a minus sign, and, there should be a hat there. Okay, and so because it appeared with a minus sign, we want to minimize this quantity. Jensen's inequality tells us that whatever this is, it's bigger than that quantity there. And so what would be ideal is if we could take y hat, which is, we're thinking of as a realization of this limit random variable for the diffusion on the simplex y to actually be constant. Okay, and so we'd like our diffusion to converge in distribution to a constant, okay, which of course it won't, but as we ramp up the delta, sorry, I'll need to say something a little later. We can actually make it closer and closer to a constant by ramping up the dispersal rates, and that'll be a little bit down further. But in any case, once we've made this realization, and if it's possible to realize this, then really what we want to do is maximize this expression here, subject to the constraints that we're living on the probability simplex. And this can be achieved by, all we have to do is find the pi that does this and then take as our dispersal matrix a matrix of the form delta Q, where Q's a Markov chain Q matrix that has the pi transpose as a left eigenvector. Remember I said we were dealing with column vectors here, even though for probabilists we'd be more comfortable dealing with row vectors. And so we just want to find such a guy, and then we can get closer and closer to this ideal situation by just ramping up the rate delta. And one thing to realize is that pi may be on the boundary. So in an ideal situation, there may be some patches that you just don't want to visit, that you want to stay around some. So here's an example that suppose that again patches are independent, and we've got some diagonal entries, and then the optimal dispersal probabilities are given by this probability distribution here, and that's this really is something that well, it always adds up to 1, these guys, but of course we also need them to be non-negative, and they'll be strictly positive if this condition here holds. And so one can see that all patches will be visited, provided that these numbers are small compared to the variance parameters. So all patches will be visited provided that the environmental variation is sufficiently great relative to the distance between things. Okay, here's just another quick example here where the variance covariance matrix is something where things are completely exchangeable. Okay, and so there's a variance parameter and a covariance parameter. Okay, single variance parameter, single covariance parameter, because everything's exchangeable, and we just sort of write the covariance parameter as the variance parameter times a correlation coefficient. Okay, in that case, if we just let mu hat be the average per capita growth rate over all, this is the average per capita expected growth rate over all patches, then one can come up with again a formula for the optimal dispersal distribution that will involve things here. Okay, and here's just a sort of a numerical example to also give you sort of a flavour of the kind of thing that goes on. Over here, what we've got is 10 patches, and each patch has a mu parameter and a sigma squared parameter, and there's also a constant correlation between patches. Now, this graph here with the open circles graphs the sigma parameters. So, there's less variability out towards the edges. This graph here has the mu patches. So, expected growth is positive towards the middle, negative towards the outside. Okay, now when the patches are negatively correlated, everyone wants to stay in towards the middle. And the scale's a little bit off here. But in fact, if all patches were being used, there'd be 10 bars. There's only 6 bars here. So the first 2 patches and the last 2 patches aren't getting used. Right? Okay, now here, if the patches are independent, 8 of the 10 patches are getting used optimally. The 2 outside ones aren't. Now if you ramp up the correlation so that the correlation between things is a half, all patches get used, and in fact there's a preference for being out towards the boundary. So it's sort of really quite remarkable, the effect that just changing the correlation can have on what's the optimal thing to do. Okay, so that's this sort of situation of, if organisms were to behave, kind of ideally, what would they do? let's sort of consider another situation where, in fact, we don't allow that, and so the dispersal matrix and the environmental parameters are given to us, and we can't just change them, and we want to get back to the original problem of computing the Lyapunov exponent. And in general, that's not something that there's just a formula for, but we can get a useful approximation if we think of the dispersal matrix as being a multiple of some fixed generator matrix Q and letting this parameter delta go off to infinity. Okay, because as a mathematician, it makes your hair stand on end to see delta going off to infinity, but because the biologists like using that for a dispersal rate, you're sort of stuck with it. And so, well, you can get a handle on this by just doing sort of an approximation. Well, the first thing to do, just for simplicity of notation, let's just let epsilon be 1 over delta. Okay, and at least epsilon is small, so that's good. And now let's try to solve this equation here. And this is something that can be solved uniquely. Now, of course, Q in general is singular, but, that's not a problem here. This matrix is in the range space of Q transpose. So it's this can be done. Sorry, this vector here, I should say, is in the range space of Q transpose. Okay, and then one can prove a little sort of diffusion. Well, I mean, we started with diffusions, but the diffusion that we started with, if we subtract off this mean here and then rescale suitably and also change time suitably, then we get convergence of the renormalized process on the simplex now to a process that lives on Rn, and it's something nicer, right? It's just an Einstein-Uhlenbeck process, right? No nasty stuff out in front of the Brownian motion, and some linear stuff in the drift. Okay, and so then by standard facts about Einstein-Uhlenbeck processes and their stationary distributions, one gets an expression that says, well, chi of delta, well, this is what you'd get if you just sent delta all the way to infinity, right? Because when delta goes all the way to infinity, the y hat variable random variable will just be the constant pi. And then you get this sort of first order correction here, okay? Which in principle involves doing this integral here. This is coming from, I think it's called Cayley's equation. People will probably correct me, but it's, this kind of equation, where gamma and B are given and you want to solve for A. So it's a matrix equation that's linear in A. People know this, they show up in control theory all the time. It's Lyapunov's equation, is it? Because there's, if we had a different matrix there,
Well, if B is positive, and then you can solve it for positive matrix A state.
that's what's called Lyapunov's equation. Good, yeah, I know that various people's names are associated. Okay, and so, we could do this approximation when we've got, again, sort of fully connected patches, this completely symmetric situation in terms of the variance. Okay, so here, the covariance structure is completely symmetric. The dispersal strategy is completely symmetric. This just, remember, is the Markov chain that at rate 1 over n, an individual sort of picks at random from the n possible states and goes there, including possibly staying where they are. And so, of course, the stationary distribution as pi in this case. Okay, and then when you sort of plug in the details in those formulae, you do get an answer, and the answer involves kind of the variance of the mu parameter. And so by that I just mean, sort of this thing here, sum I equals 1 up to n mu I minus mu bar squared 1 over n. That's what I mean by the variance of mu. And so what you see by looking at the signs here is that for large delta, the Lyapunov exponent's going to be decreasing when there's too much variability in the expected growth rates compared to the stochasticity in the problem, right? So doing too much dispersal will be counterproductive in that case. Also, if this equation here holds, and we look at the difference between what the growth rate is for essentially no dispersal and the growth rate for, essentially infinitely much dispersal, then this will be positive. And so this says, out near infinity we're decreasing. At 0 we're bigger than where we are at infinity. And so it's kind of believable, although not proven, that we're actually decreasing all the way from 0 out to infinity. So, just more dispersal's always bad for you. Okay. Similarly, here's again this. We had this same situation here, but now we're going to look at a slightly different regime for the parameters, and it's not sort of too important what this is here, but it's something that's completely sort of interpretable in terms of what's going on physically. Then in that case, one can see that the Lyapunov exponent is increasing for large delta, and the value at 0 is bigger than the value at infinity, and so that must mean, well, it doesn't mean that it's just bowl-shaped, but it does mean that the best choice of the dispersal rate is going to be somewhere between 0 and infinity. So here, did I say best? Worst. Yeah. So that actually, the growth rate is minimized somewhere in the middle. That there's somewhere in the middle that's worse than doing no dispersal or, infinite amounts of dispersal. And, just a comment about what this means, sort of in words, that there's just a few patches. Most patches are very similar in terms of their per capita growth rates, but there's a few that have, really high per capita growth rates. Okay, so now sort of a slight change of pace to some group theory. So I hope this is a refresher for everybody. Everybody remembers their representation theory. So, we've got a finite group here, and people remember that, representations, well, it's just like, growing up Fourier series, right? The great thing about, Fourier series is that it sort of turns addition into multiplication, which doesn't seem like a good thing to start with, but of course it turns, sort of convolution of probability measures into, products of Fourier transforms. Has anyone here read Tom Kerner's Fourier analysis book? And the great quote about the central limit theorem in there, which is, he proves the central limit theorem and then has this quote that, the ease with which we proved the foregoing theorem is an indication of why Fourier methods hold the place in probability theory that in other branches of mathematics is held by thought. Which is, you've got to admit is kind of true about some things, right? You go to Fourier land and then just mess around. And okay, so, you know, in a general group G, rather than sort of a thing that is something, it's a homomorphism from G now to a group of matrices, not just to the real numbers. So, you know, it's something that turns, you know, multiplication into the group into ordinary multiplication of matrices. And then, you know, for any such representation, we have a function from A to the reals, or more generally the complex numbers. We've got its Fourier transform. And, you know, the great thing is that if we know the Fourier transform of a function, we can recover the function by doing Fourier inversion. And so this is, you know, just what Fourier inversion looks like in this world. Here the sums over all so-called irreducible representations, and, you know, sort of irreducible representations are, you know, just like irreducible Markov chains, they're, you know, ones that aren't, when we look at the matrices, they aren't similar to upper triangular ones, right? That's irreducible actually means the same thing as we mean by irreducible. And it's true that if the function A is a so-called class function, that is, it's constant on conjugacy classes of G, then when we compute this thing, which in general will be a matrix, we actually get a constant multiple of the identity matrix. And in that case, we just use, you know, A hat rho for that constant that's out the front of the identity matrix. Okay, now, you know, why bother with this stuff? Well, we sort of bother with it because, you know, it has the same role of, you know, making it easy to understand convolution, right? So that's you know, it allows us not to do any thought, just like Tom Kerner said. So now let's sort of suppose that, you know, our patches, we can think of them as being sort of elements of a group. And, you know, I mean, what sort of group you might ask yourself, because I'll talk about that a little, but, you know, just, you know, the integers mod n, right? So you just imagine the patches round a ring. And, you know, this isn't so fanciful. There's actually species that are called ring species that are sort of, you know, that's how they're sort of distributed. The Central Valley of California is, you know, sort of a miserable, hot kind of place, but it's actually rather hospitable round the outside. And so there's certain species that kind of live in a ring round the outside and, you know, can only kind of interact with each other by, you know, observing the sort of circular topology. They can't cut across the middle. And, you know, let's just suppose that our rate matrix Q is of this form for some function little q, and the variance covariance matrix also respects the group structure. So, you know, this just means that the Markov chain that goes with Q is just a random walk on the group. Okay, and if these guys actually turn out to be constant on conjugacy classes, that, you know, kind of horrible looking integral that was giving our approximation for large delta for the Lyapunov exponent is something that one can compute, you know, fairly concretely in terms of Fourier transforms of things. This just means the Hilbert-Schmidt norm of this matrix. Remember, this guy's a matrix. Because Q and S are class functions, they're constant on conjugacy classes. Their Fourier transforms are constant multiples of the identity, and so that's just what these things here mean. And of course, S, because it's a positive definite thing, it's going to have a Fourier transform that's a non-negative number, right?
Sorry.
Yeah.
You said that patches are elements of finite group. What's the operation of this group? How you define this operation?
just whatever the group operation is.
But for patches, how you define? What is in reality?
Well, I mean, it's just here, you know, if your patches were like this, right? Right, it's just saying that, you know, it's really just saying everything's rotationally symmetric. It's not saying anything more than that, right? I mean, it's sort of like Sergei's example yesterday with the three queues, right? The three servers. You could.
Is commutative or not?
Doesn't need to be commutative, otherwise I wouldn't have to worry about the going to matrix valued representations. But I'm just giving you an example of a situation where, you know, one would want to sort of do, you know, work with a group valued setup. And so, you know, that's exactly what one can do here, is sort of work with, you know, the patches all in a ring, and so we can just identify them with the integers mod n. And so when I said everything's symmetric, of course we don't want everything to be symmetric, or it's, you know, there's no interest, right, if every patch is the same as everyone else. So what happens is that there's actually one patch where the expected growth rate is a little higher than all of the others, right? So patch, if we think of these as the numbers 0 up to n minus 1, patch 0 has a little higher growth rate than the others. Okay, now we're jumping around between patches according to a random walk on the integers mod n. And so that's going to be governed by these probabilities p0 up to pn minus 1. So when we turn it into a Q matrix, we have to subtract off, you know, the total jump rate. And let's just suppose, to make things even simpler, that our jumping is symmetric, going to the left and going to the right is, you know, because the subtraction here is mod n. That they're, you know, treated equally. And let's just suppose, this is just saying that our variance covariance matrix is some perturbation of the identity matrix. If we just had 1 here and all zeros, then that would be the identity covariance matrix. And then just reminding you how Q and sigma hat sigma are sort of built out of this story. Okay, and, you know, one of the reasons we sort of went to this story is that it actually, apart from the fact that there really are organisms that live like this, is that one can come up with, you know, a rich class of sort of analytic examples where what one has is that the optimal dispersal is for intermediate ranges of delta, that some dispersal is good, too much dispersal is bad. So this is saying no dispersal is worse than infinite amounts of dispersal, but this guy decreases for large delta, and so, you know, in principle it's looking something like that, the chi curve. Okay, and I'll sort of just wanted to sort of put up sort of another picture about, you know, why this sort of general group story might be of interest, and that's for sort of cases where there's a hierarchical structure. And so one of my co-author's colleagues, she works with butterflies on islands up off the coast of Vancouver. And so, you know, the butterflies, you know, have a whole bunch of meadows on each island. And, you know, so they wander around the meadows, and then they can every now and again wander between islands, right? And so that's the sort of situation here. The stars are the patches, and then, you know, these two patches are grouped into, you know, we could say like a block, right? these two blocks are grouped into a suburb, and these suburbs are grouped into a town, and so, you know, very rarely you'll jump between suburbs. Perhaps it's more likely to, you know, jump between blocks, you know, and then within blocks, it's even more likely to jump between patches within them. And so this we can think of again as having a group structure. In this case, I guess it's what, you know, integers mod 2 cross integers mod 2 cross the integers mod 2, and so one can use the group theoretic analysis, the representation theory analysis to, you know, understand what goes on here. And let me just finish, whoops, by concluding that, you know, there's a huge amount of work in this area in the ecology literature, but it's almost all done by, you know, simulation with, you know, very particular choices of parameter values, etc. And so, you know, suitable probability models can shed some light on how dispersal and environment interact with each other. I'm surprised I haven't got this question already, you know, given sort of the hard time that Sebastian got about, well, if you've got a supercritical branching process, you know, shouldn't everything have exploded? But, you know, in these models we haven't accounted for, you know, the effect of competition for resources. So talking about this asymptotic exponential increases, you might think somewhat fanciful, but, you know, the models, for one thing, can be thought of, you know, kind of linearizations of these sorts of models that apply where there's, you know, relatively few individuals around. And also one can prove quite general theorems that say, you know, if the asymptotic growth rate is positive, then when you do put in competition for resources, that translates into a stationary existence of a stationary distribution, whereas, you know, asymptotic sort of exponential decrease translates into eventual extinction. And so the real thing is about understanding the linearization of these models around zero, which is exactly what we've done. Okay, thank you.
Yeah, a question that's related to your last comment, or
Right.
on the conclusions that are that
Right.
you know, there's this, as you know, there's this controversy within the ecology community whether the spatial component is really relevant or not, because a lot of these guys just want to write down ODEs and not worry
Right,
about
and
that.
do, yeah.
And so, and as you mentioned, it's mostly simulations where you,
Right.
the thing is with the simulations that they take into, do they take into account more factors than you're doing here, or is it essentially just identical environments
So
that are correlated in some way?
A lot of the simulations really are just multiplying together random matrices. You know, so exactly the sort of, you know, you kind of discretize the sort of model that we had here and, you know, multiply those guys together. That being said, the random matrices in that setting are what are the coordinates represent. Sometimes they represent more than what I had here, which is just spatial locations. Namely, they're the so-called Leslie matrix things, where you sort of think about individuals, you know, progressing through life stages, right? So, you know, how many individuals were born, and then, you know, something happens to get them to be juveniles, get them to be sexually productive, blah, 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 right? And so they do that kind of thing. So, you know, the thing with that is that, you know, you can be kind of endlessly inventive in the simulations, but it gets harder and harder to draw sort of global kind of conclusions about things the more detail you put in. And the second thing is, you know, when you sort of saw like the acorn woodpecker data there, you know, there's the data, you know, is really sort of pretty crude. You know, it's not like, you know, Ruth's, you know, big Xerox machine, right? You know, you don't go to, you know, this canyon and sort of feed it through a flow cytometer and it sort of instantaneously counts all your woodpeckers. And so someone's got to go out there and actually watch for a long time and try to count things. And so, you know, getting enough data to fit, you know, fancier models is just very difficult. And so, you know, there's this trade-off between, you know, it's just, you know, I could be giving this same talk after just about any applied lecture, right? But there's always the trade-off between, you know, how detailed the model is, how easy it is to draw general conclusions from simulations, et cetera, right? And how hard it is to fit it from data.
I like your symmetry approach, your group theory approach, which requires your matrix Q and your covariance matrix to be invariant.
Right, yes.
Is there some mechanism which in a real ecosystem would lead to this symmetry between patches?
Well, you know, we sort of hope that, you know, that if in this sort of situation, so this is, you know, because this says, you know, for example, you know, these guys all have the same variance parameter, right? Variance of this is this is this. So, you know, correlation between these guys is the same as the correlation between these guys. The correlation between these guys is the same as the correlation between these guys. And so you can sort of imagine, for example, if we were just at two levels, like I was saying about the butterflies and the islands, that, you know, you might have two islands and a bunch of meadows on each island. And so that, you know, within an island, the meadows, for example, could be all essentially exchangeable. And then, you know, between the islands, the same thing, right? That, you know, I mean, of course, you know, if the islands are really long and thin and, you know, sort of they butt up against each other like that, then that's not reasonable. But if, you know, when a butterfly, you know, leaves this island and alights on the next island, it's, well, that's talking about the Q story. But in terms of the sigma stuff is sort of coming from environmental things, right? And you'd sort of imagine that, you know, rainfall patterns and all that sort of thing might be fairly similar within the islands. And so, you know, taking the stochasticity to have that sort of symmetry, you know, might not be too sort of outrageous. It's just, you know, this is sort of a tool that lets you, you know, in the middle of all of this, you need to, you know, there was a mention there of generalized inverses of matrices and integrating sort of matrix exponentials and things like that. And, you know, in general, one would just have to do that numerically. And then there's always the question of, well, were the parameter values you chose, were they reasonable, all that? Whereas this lets you draw, you know, kind of general conclusions at the risk of, you know, further stylizing the description of what's going on. And so that's the price one pays.
Yeah, if I'm understanding your model, you're basically ignoring, you know, sort of normal or population fluctuation. It's not a branching process model.
No. So what it is it's a, so, and in particular, it's not a, you know, again, as Maury was saying there, how, you know, the thing about spatial variation important, you know, there's also the fight in the biology literature about is, you know, discreteness important, right? You know, the fact that, you know, if you have an ODE model, it will let you get down to having, you know, 10 to the minus 8th individuals and then recover, you know, that, and then explode. Well, that probably means that in real life, when you can't have fractional individuals, that you'll die out, right? And so that's how you'd want to use branching processes.
But if you're going to, if you're going to try to use this to analyze data,
Right.
and particularly things like your woodpecker data,
Right, yeah, so there,
you've
discreteness
got
is-
relatively,
yeah.
well, forget even
Yeah.
just the relatively, in the butterfly world, things may not be discrete, but
Yeah.
you're still going to have, I would think, even if your environments were perfectly constant in both space and time, you're going to have fluctuations in the population. And so how are you
Right.
going to distinguish between the fluctuations
Right.
that you would get just from the ordinary fact that populations are reproducing and,
Right.
and possible
Yeah.
fluctuations?
Yeah, I mean, this is sort of saying that there's this kind of background effect that's lifting all boats similarly, but it is, one way of kind of saying that, I mean, it is getting at the same kind of thing, though, right? It's just not, I mean, it is allowing there to be stochasticity in, numbers from year to year, not just sort of constant exponential increase. It's just not getting at it via an explicit branching process model, that's all.
Last
but-
question, maybe?
Okay, go ahead.
Right, there's no other last question then, please.